Hello guys, welcome back to the DP design. Hope you are all doing well. So today we are having a session on the flow simulation of a turbocharger. Also in this video we are not focusing on the mathematical calculation of the turbocharger. So we will make another video. So if there is any requirement on that, so please comment down your requirements and I will make a video on that. So this video only focus to the basic methodology, how to do a simulation, how to do a basic boundary condition, how to give a rotating regions in SolidWorks. So in this video, you are seeing a basic visualization after the results we are getting. So this is how flow trajectories works. So we will start a basic like from the zero, how to do let's get started without wasting any more time, right? So I'm closing this and I will start. I have this model. So I have a turbo model, then without results, and I will select the assembly. Okay. So in this model, you are saying this that the openings are not properly closed. Also, this is a watertight model. So if I am hiding this, so this portion is connected to my exhaust region, and this one is the exhaust outlet, and this one is a compressor compressor wheel, and this is a compression housing. I have hidden this, so I will hide these components which are not necessary right now. Okay, so this is the housing of the shaft. I will rotate this, so you have to make a compressor wheel and turbine. Okay, so this one is a turbine housing, and I will show all components. Go to the show hidden components. I will select all the parts, exit. Okay, so first we have to close all the openings, just like the exhaust and the inlet ones. So I will close this using leads command. Create leads, go to create and select the surface, and I will create a 1 mm of lead at each portions. This one, this one, and this one. Okay, I am done with it. Now I will hide this part. I will hide this part. Also, if you are known, if you know the top-down assembly, it will be very easy to understand the rotating regions. So I will create a one part, a new component, go to the new component. And also, my component is created right here. So I will name it a rotating region. Okay. I will edit this and I will create a rotating region around this compressor and turbine. Okay, so I will sketch on this plane right here. Go to sketch and I will revolve around this compressor and turbine. So you must cover all the components of the compressor while you are making a rotating region. So I will basically create a gap of a 1 mm. And also this one. Okay. The top notch surface having 1 mm of clearance. Also, this part having a clearance of 1 mm. Okay, done. Now I will use the revolve command. I will select the axis, this one. So you can see how my rotating regions have created. Okay, so I will create okay. Yes. So here you can see my major components, like I have closed the opening, I have created the rotating regions. Now I will go to the flow simulation, the environmental properties, boundary condition I have to give. So let's move on to that. So basically I will, first of all, I will change the transparency of these rotating regions, and also these leads. I will change the transparency. So it will easy to understand and visualize. If you do go to the flow simulation first, then open the wizard. In the wizard you can name your project. First I will name it Turbocharger flow simulation. Okay, so I have not many configuration for this type of simulation, but you can use the different kinds of configuration, like the according to the compressor geometry and turbine geometry. So you can create your own configuration by changing the dimension of turbine and compressor. So this is the unit system I'm taking. For the pressure, Pascal. Okay, done. For the velocity, I'm taking meter per second. Okay, and here you can change all types of units right here. Okay, next one. This one is a internal type of analysis. In the last video, we have done the external analysis for the aerodynamic purpose. You can check out the Formula One simulation which we have uploaded. So in this kind of simulation, we will go for the internal one, and I will extrude the cavities without a flow condition. Okay, the fluid flow check, the conduction. We are not talking about heat right here, but okay, the conduction is off. So if you want to do a time dependent analysis, like you want to do it for a 1 second or 3 second or 5 second, so you can check it here and you can total analysis time. You can input your time, like I have to do a 3 second, and output time step. I will take a zero point 0.1 step time. So that's how you can do a transient simulation, but it will take a very long time to solve. So I have done this for a 1 second, and it took more than 2 hours. So I will uncheck this. I will only depend on the iterations, the computational time. So you can check your gravity if needed. Okay. So I'm focusing on the less consume like less computational time, just for to understand the basic methodology, how to do it. So I will, in the rotation there are three types of region you can select. In the global rotating there is no need of uh, the body, the closing ones. So you can use the global rotating for the windmill type of simulation. The sliding ones is like a dynamic meshing, the mesh moving. So also it will took a very long time for solving. So I will take a local region averaging method. Okay. So you can do choose the different rotation regions according to your requirement, or according to your functional requirement, right? So I will check next. Next here you can select the gases. So I will select the air. Okay. The flow type. Okay, laminar and turbulent. I will check. Okay, yes. Humidity I don't need. So roughness, no, I will not. Oh, the turbulence parameter you can give if you want. So I will finish. So I'm done with the environmental condition for now. So here you can see your computational domain has been created. I will increase this computational domain according to my simulation region. So my simulation region will be this, and I will okay take this lead into the computational domain. So okay, computational domain, and I will increase here, here. Okay. So here you can see, yes, I have done the perfect computational domain, and I will hide this. Then now, now we are talking about the boundary condition, which is very important to give, and also the rotating regions, how to specify them by selecting. So here is your exhaust. This port is connected to the exhaust, your engine exhaust. Okay, so the air, exhaust air will come from this, and this will rotate like this. So basically, we will give the RPMs, the rotating RPMs in this direction, and this one will be my environmental condition for now. And if you have done the mathematical calculation for the exhaust air exhaust outlet from the engine, so you can input your inlet mass flow here. So I will assume 1 kg per second for this simulation, and here you can see here your intake mass flow air, and this will go right here, and it will compress the air to the engine from this port. So for a second I will show all components. Yes, the flow will be like this, and it will out from this, and the intake flow from this and out from this to the to the direct engine port. So I will exist. Now, now I will give the rotating regions. I will select the insert rotating regions. Now, rotating regions, I will select the outer cylindrical face. Oops. So there's a mistake I have done from creating. So I will increase the size of this rotating region. There's no need to worry if you have done any mistake to create. Okay. So I will check this in a, where's my rotating region part? Okay. Now I will edit the component. So what is happen? Okay. Now I will delete the dimension, and I will increase the length. So the distance delete. Okay. Done. So here's a warning. If you change any geometry, there is a warning. So the model geometry project has been modified. Do you want to reset the computational domain? No, because it already in the computational domain. So yeah. Okay. So you can see there is no error. Now I will go to the flow simulation from this feature manager tree. Okay. Now I will select the rotating region. Inside rotating regions, I will select this one. So I will give a 50. Here you can see the rotation will be in this direction. Okay. So if I want to give the rotation in opposite direction, so you have to give a minus sign for the opposite direction. So I will create a 1 lakh RPM. So if you input the RPM, it will directly convert it to the radian per second. Okay. Now you can see your direction has been changed. Okay. Now I will correct this. Good. So my intake flow, like exhaust flow, will be like this, and it will rotate in this direction. So I will check OK. Now the time for the main boundary conditions, the intake mass flow, and the environmental condition. So I will insert a boundary condition. So now on the boundary condition, go to the insert boundary condition and inlet mass flow. So basically, it is coming from the exhaust of the engine. So if you have the mathematical calculation, you can input right here. So I will select those phases where I have to give the intake mass flow. I will assume it will be 1 kg per second for now. Okay. And I will create this as an environmental condition. So go to the pressure openings and select the environmental pressure right here. So you can customize this pressure by selecting the static and total pressure. You can change if you want. And also I have explained about the rear wall and ideal wall difference in the last video where I have done the Formula 1 aerodynamic simulation where I explained the detailed study about the real and ideal wall. So you can check out those video for the more information. Okay. Now, now insert the boundary condition for the intake. So I will select right here and I will give a intake mass flow around 3 kg per second. This will be my intake to the engine port. So this port is directly connected to my engine cylinder. Okay. So I will select this phase for the environmental condition where I can measure the pressure, the velocity. Okay. So I am done with the environmental condition and the boundary condition. Now the next step is to select the goals. How much mass flow rate is varying? Okay, the pressure difference it can create in the compressor and turbine regions. Okay, so that kind of plots you can select. So I will show you the brief. So if you want, I will delete this one and go to the goals. You can select the surface goals, the point goals, the volume goals, and equation goals. Also, I have explained the equation goals to find the drag force in the last video. So how to make an equations. So you can make equation for the turbocharger as well. You can put out any mathematical calculation and select all the boundary condition right here. So according to that, according to the results, it will change the values and you can directly take the uh, many iteration results to compare. Yes. So go to the global goals. Here you can select the parameters if you want to check. I will not check because I want a less computational time to compute. Okay. Go to the surface goals. Point goal is I am not using very. So here you can select any point and it will directly show you the results at particular point, how much pressure there is, how much velocity, how much pressure difference is creating. I will go to the surface goals and I will select the surface, a particular surface, any kind of surface in the part that should be that should have to in a computational region for to compute the goals. So I will create one mass flow rate. Go to the mass flow rate and maximum mass flow rate right here. Okay. So yes. So here you can define many types of goals. Okay. So in the mesh you can select the customized mesh. So I will select the basic mesh, which is very coarse and which will not give you a proper results, but I will uh, insert a local mesh and here you can define the cells according to your functional requirement. It will take a lot of time, but still you can do it for the accuracy purpose, for the accurate results. So I will check okay, then I will go to the run. Okay, so use all the batch results. Yes, the surface plots. Right. So here you can see preparing model for the simulation, the mesh refining. Okay, the list of goals I have selected, it is computing the values. When it will be 100%, it will, yes. So this kind of plots you can see at which iteration how much pressure is generated, how much velocity. So for that kind of plots, you can select from this icon, and you can select the front plane. The also you can select the any surface for from the part. So I will create a front plane, go to the settings. Also you can take the offset from plane. The contours, the ISO line you can select. So I will check the ISO lines for now and go to the settings. I will select the velocity, and you can select the size of your image. Okay, so I will just select the 640 by 480. Go to the option. Okay, after if you want to save every image at a particular iterations, so you can check this save image, save video. Also you can check your mesh size if you want. Okay, so this is how it will plot. This is the velocity plot. It is changing according to the iterations. You can see the minimum velocity and the maximum velocity it is creating, right? So I have now 70 iterations, 72. You can check the pressure, list of goals. It will, okay, the 50, 18%. Okay, it is about to complete. Okay, my solver has been finished. Okay, solver finished. I will close this. And here you can see my results are loaded. Now, these are the plots I have created before. I will delete those plots and I will explain. Yes, I will delete these plots. Okay. Now, if you want to see the results, I will take a cut plot in the select the yes top plane, give a contours and ISO lines in the velocity. The ISO lines will be also in a velocity condition, and I will higher number for much better visualization. Okay, so you can see how the velocity is changing according to the rotation regions and the compression region. So I will hide this. If you want to make a flow trajectories, so select the surfaces, select the numbers. I will check the 200 seats line with arrows. I will check the dynamic ones, dynamic arrows. I will 5, and the distance will be 10. Also visibility is up, okay, up 50% around. I will play this simulation. So here you can see how the exhaust flow trajectories. Okay, so that's how we interpret the results, and you can save this as an animation. The flow trajectories I want to interpret right here. So I will select those surface and I will check like 200 seats. Okay. So here you can see this is line with arrows. This is a static kind of trajectories. I will select the dynamic ones. I will select 5 and I will select the wait 10. We'll play. So here you can see the velocity has been increased at the engine port, so the your mass flow rate will be high. So this is what the function of the turbocharger. And also how to interpret the goals. So you can check the goals, insert, and we have calculated the mass flow rate. So here you can select the plot of with a CPU time or iteration or travels. So I will select the iterations and show. Here is the value of your mass flow rate at this surface, and this is the difference, the delta one. So you can export this as a Excel file, and also you can create the report right here. Go to the create report and select whatever you picture you want to add. Okay, the IDs you can create, and also you can go to the surface plots. I will select the impeller surfaces, the turbine surface. So you can see the velocity plot. Check the pressure, the shear stress, pressure. Yes, you can change for the better accuracy, for the better visualization. Okay, so that's how you do this is the basic methodology of a simulation of turbocharger. So thank you for being here till the end. And if you want a mathematical calculation, if you want accurate simulation on the turbocharger, so you can comment down right here. I will make a video on that. So thank you again, and keep supporting, subscribe this channel, and I will make videos like this and make it easy for you to simulate many things. Okay, so thank you again. Jai Hind.